just like when we dealt with integrals. The biggest question we had was not what's the value, but how do I do it? I'm asking the same sort of question about series. Which test should I use to tell whether or not a given series converges absolutely, or diverges? And there isn't a magic bullet here. There isn't an automatic, you do this every time to make this work. Instead, it depends on what the form of AN is. Now, some series, it's a matter of recognition. For example, I should be able to look at a series, look at the terms involved and say, oh, that's a p-series. But the only thing that is a p-series is something that looks like that. If it's close to, but not quite, then I can't use this. What's the rule for p-series? Almost. Yeah, I got to keep p equals 1 in there because p equals 1 is the harmonic series. I need to know that one by sight. But again, I have to see the form 1 over n to a power. Similarly, a geometric series. And if it's AR to the n minus 1, it should be starting at 1. If it's AR to the n, it should be starting at 0. But it might take a little bit of algebra to make it look like that. But again, once I see, hey, this is geometric, there's a rule. When does it converge? When does it diverge? Ta-da! Those are the first two that I hope to be able to recognize instantly. With a little bit of an around, maybe, but not, oh, obviously. I don't expect it to be obvious or intuitive right away. This is something that takes practice to recognize. So what's next? What if it doesn't look like one of those automatically? Well, maybe it's close. Maybe it's close. And if it's close to one of those two known behaviors, then maybe I can compare it to. Now, there are two comparison tests. There's the limit comparison and the direct comparison. In order to use the direct comparison test, you need to be able to write a chain of inequalities. You need to show that your series, the one you are starting with, this AN series, is either always less than some other series or always bigger than some other series. Up here, let me write that. Comparing to something else. And we'll just call that thing BN. For direct comparison, I need AN bigger than BN or AN less than BN for all N bigger than some value. It's got to be, this one is bigger from here on. I don't know which one is bigger, which one is smaller, but that's going to tell me whether I'm looking at the floor bound, breaking through the upper one. I'm looking at the ceiling holding the lower one down. So that's how to do the direct comparing. And notice that the upper series converging, that's going to be where I have this. The BN is the one I know. So I want to know if that one converges, then the lower one will converge under it. Whereas the lower one diverging is going to be the one I use here. And the bottom one breaks through the top one. But in order to do that, you have to show me this comparison. That's not always easy. So in that case, we can try the limit comparison. What's the rule for the limit comparison? Well, if the limit comparison, I take that limit and I want that limit to not be 0 or infinity. If 0 less than c less than infinity, then what? I'm sorry, I couldn't quite hear you over the fan. Well, I need to know what Bn does, right? Either way. But whether the series Bn converges or diverges, I know that the sum An does the same thing. Now, personally, I tend to prefer limit comparison over direct comparison because I don't have to show that sequence of inequalities. I can just say, hey, I think this looks like this. That's the difficult part. How do I determine what Bn should be? How do I choose this series? Well, notice what I said at the beginning of this is that the sum an is kind of like, it's close to a p-series, close to a geometric series. So I'm going to use one of those, and then I know whether Bn converges or diverges. But I have to choose that Bn, therefore I have to know what converges, what diverges from what we had before. Most often we use the dominating terms. So you use the highest power of n that's involved. You throw away trig functions because trig functions are bounded by numbers. You turn them into numbers. You look at what boundaries you can create, which really is kind of doing the inequality part. But you don't actually have to show a chain. All of the comparison tests only apply to series that are positive. Which means if I'm looking at a series that isn't always positive, I can make a series that is always positive. How? At which point, I would not only know that it converges, I know it converges absolutely. Problem. If the absolute value one diverges, that doesn't mean that the regular one diverges. Now that which is stronger sentence means if it converges in absolute value, then it converges regularly. But absolute convergence telling me about regular convergence doesn't work in reverse. If the absolute one diverges, I haven't learned. But as soon as I say, hey, the absolute one diverged, well, then maybe I should check for divergence. How do I check for divergence? There's a test that's specifically called that.
Limit as n approaches infinity of n doesn't equal 0.
In order to converge, my terms have to get smaller, infinitely smaller. If they don't, then we can't possibly converge. If I'm looking at things that have changes in sign, this will be helpful, because then my limit might flip back and forth between a positive thing and a negative thing, as opposed to settling down to one number. And that works in the alternating idea in general. So let's suppose that my sum has a -1 to the n and then stuff, or a -1 to the n plus 1, or a -1 to the n minus 1, some -1 to a power of n. Well, then that's the definition of an alternating series. So we're going to use the alternating series test. What do I need to check for the alternating series? I'll be right back. Yes, sir.
We get b sub n plus one grade exactly with less than or equal to b sub n. Also seeing a zero limit.
Aha. Now, Bn was not defined in this version, but what's Bn?
Like what I'm comparing to zero.
That's true up here. But in this version, this test, Bn is, Dominic? So that's the stuff that I've written here, right? I didn't even use the phrase Bn, I just used the word stuff. So what I need to show is that the stuff is decreasing and that the stuff has a limit of 0. I chose to use the word stuff instead of using the phrase Bn, simply so as to not confuse myself. But if you want to use that, then the two things I need to check is that the stuff is decreasing and the stuff has a limit of 0, and then the sum converges. And I wrote -1 to the question mark there because it doesn't matter which version it is. Whether it's an n plus 1, or an n minus 1. If it's an alternating series, now that does not say converges in absolute value. That's not absolute convergence, that's just convergence with the signs. I tend to do the limit before the decreasing because decreasing is usually harder and might involve taking a derivative. Personal choice. What else? What's next on my list? Things that don't quite alternate but still change sign. If I see factorials, I'm most likely going to use the ratio test. However, if I have like a cosine of n and a factorial, I may need to do comparisons with those things. If I have e to the n involved in there, I may need to do a comparison instead. It might be a little more difficult to do the ratio test if I see algebraic functions of n. But it may still be the right test. What does this test say? There is a test called the ratio test. Yes. What is the ratio test? What do I do? Nora? Bingo. But there's more. What if L is not less than 1? Great. So I take this limit, and I'm actually getting absolute convergence as a result here. There are really only 2 more tests left in front of me of the things we covered. Number 7 is the root test. But the only time I'm going to use the root test is when an looks like that's what the test is. But when should I use it? If I'm going to take the nth root, if I've got stuff with an nth power. And again, Nora, you're absolutely right. I take the limit as n goes to infinity of the nth root of the absolute value of an. Call that L, and then treat L just like in the ratio test. What's the only other test sitting in front of me that I didn't talk about? And why didn't I do integral tests? Because integrals suck, right? That's the last thing on my list. Actually, it's technically second to last. The integral test is only going to be helpful if I can write an as some function where f is positive, decreasing, and continuous, and the integral 1 to infinity of f of x dx is easy to do. If that integral turns out to suck, I don't want to do the integral test. But doing that integral may actually give me the correct result. What is the result of the integral test? If all of those things are true, what do I do when the integral test itself?
Just need to get a number or infinity. It's infinity, I know it converges.
And if it's a number,
It converges.
and therefore so does the series. So just like in the limit comparison test, getting a number in and of itself is not the end of it. I then have to say, well, what happens to my series? If the integral works out, then the series works out. Last but by no means least, there's one other possible thing I can do. And actually try and find the partial sum. Now, that and geometric are the only two where we actually get a total. If I'm doing this, I can come up with the actual result. What's the limit here? And then the limit of Sn is my sum, capital S. In the geometric series, what was our total? I didn't write that one down. What is the actual sum of the geometric series? Almost. Not 1 over 1 minus r. It's a over 1 minus r. And since I call that S as my sum, I'm going to do the same thing here. And get a sum S. Those are the only two ways we can actually get a total. Everything else just tells me, does it converge or does it diverge? It doesn't actually tell me what it converges or diverges to. Oh, crap. On our Canvas page, I put up 2 different handouts, one of which is a flowchart. The other of which is a handout by Dr. Kaminsky that both say series tests. Download this, take a look at it. This runs through all of the options we just did. Is this short? Is this obvious? Hell no. But this now gives me a method by which I can start trying to tell, does this converge or diverge? As with our integrals, which test did we try depended on what the series looked like? Well, now, what test I try depends on what this thing looks like. And that means it's time to do a crap ton of examples so we can see what we should be trying. Here is a series. Let's try and address this in order. Is this a p-series? I got other stuff in there. I don't just have n to a power. Is this geometric? I'm not using n as a power, and in my geometric series, it's either r to the n or r to the n minus 1. That's not going on here. And it really doesn't kind of look like either of those. So I don't think a comparison is the right way to go with a geometric or a p-series. What was option 4? What happens as n goes off to infinity here to the term an? And last time I checked, 1/2 is not 0. And if it's not 0, this diverges. That was convenient. Ew.
Which I do a p-series, I comparison, I do a comparison test.
Yeah, but why? Wait a minute. If I think about the dominant terms, the biggest term at the top and the biggest term in the bottom, in the top, that +1 isn't really going to matter once n gets pretty big. And in the bottom, when n gets really big, n cubed is much bigger than n squared, and therefore much bigger than 2. So really, my brain says, if I only look at the parts that matter, I have that. Well, wait a minute. I don't even need the 3 on the bottom. But just think of it, the powers of n. Let's ignore the 3 too. Well, wait, if I simplify that, that's n to the 3/2 on top and n cubed on bottom, and that's 1 over n to the 3/2. That is a p-series. Now, this is where people usually look at me and go, right. This expression is all sorts of messed up. But in essence, when n is a large number, that's the only part that matters. That's a really non-intuitive statement. Shouldn't the rest of these pieces take over? No. as n gets bigger and bigger and bigger, n cubed is what this looks like. As a matter of fact, if you graphed this and graphed this for x n fairly large, you'd see that those two curves were almost exactly parallel. That's the critical piece, that these are behaving as parallel ideas. For those of you who have taken or will take discrete math or computer science algorithms and algorithmic complexity, that's what this is all about. This is order of complexity. What I've really done is stripped everything that's less powerful out of the function. So, Leo, I'm going to do that comparison test. But before I do it, you need to answer me a question. Does that series converge or diverge?
That can vary by p series is greater than 1.
Now, I did not show a chain of inequalities. So I'm not going to do a direct comparison test. I'm going to do the limit comparison test. And that means I'm going to take a large and fairly ungainly limit. The limit, as n goes to infinity, of an over bn. You know what? I think I'm going to write this limit with this. So instead of 1 over n to the 3 halves, I'm going to write n to the 3 halves over n cubed. Now, why would I do that? Because I am a sick mutt? Well, yes, but that's a separate issue. Because you take this out of the bottom and you flip it over. Now, why does that make things better? Because you're multiplying things, right? Multiplying on the top and I'm multiplying on the bottom. Does it matter what order you multiply things in?
Multiply each of them 1 over I think they're going to top.
I'm sorry, say that again?
You're going to multiply the top.
I don't actually want to multiply at all. I want to rearrange my multiplications. I'm going to take these two terms and switch their order, just on the top. Now, why would I do that? This is algebra parts. So I'm actually going to do these two limits separately from one another. The limit of a product is the product of the limits. Chapter 2. Whoa, we're really digging back into the past. Please note, the top of that expression, n cubed plus 1, is under a square root. The bottom is a square root also, isn't it? So I'm going to write that as the square root of n cubed. What possible benefit has this algebra gotten me? Leo?
It's like on way we can, you have the like terms, and you can like say the limit is like 1/3 times 1.
Aha! This is a fraction with the same power on the top and the same power on the bottom. Those cancel, and I get 1/3. This becomes the square root of a fraction just like that. So the limit inside the square root is 1. Okay, I have now finished doing the test. What is the result of my test? Exactly. 1/3 is a number between 0 and infinity, not including 0, not including infinity. Both series behave the same, which means both series converge. And since I knew the p series converged, I now know that the other series, the one I wanted to know about, also converges. Yes, Maddie?
Why did you do just like? Why did you just switch?
Does it order matter when you multiply? Ah, sneaky little algebra trick. I have a over b times c over d. If I do that multiplication, I get ac over bd, right? Which is the same thing as ca over bd, which is c over b, a over d. All I had to switch was the tops. The hardest part of a calculus class is not calculus, it's algebra. Before I even start at the top of my list, I see an exclamation point. Where should I jump, Jan? Exactly. I should jump directly to the ratio test. So let's try that first. So limit as n goes to infinity, a n plus 1, so that's 2 to the n plus 1 over n plus 1 factorial over a n, 2 to the n, over n factorial, all inside absolute value. Fractions within fractions suck, rip it and flip it. what happens here? Playing with factorials is important.
I know you can do like the 2 to the end and stuff, but you just cancel it out and like leave it to.
I will leave a 2 on top. So when these cancel, that leaves 1 2 behind on top.
You just have it n plus 1 on the bottom.
That-
Factorials will cancel out.
Because n plus 1 factorial says take all the numbers from n plus 1 and multiply down, but the next number down is n. So all the numbers underneath n plus 1 are n minus 1, which is the same as the n factorial on the top. So they cancel, and I'm only left with the n plus 1. What is that limit?
That means 0.
I hope so. 2 over something gargantuan, that's 0. 0 is less than 1. So, what is my conclusion? Say again? Almost. Ratio test doesn't just give me convergence, absolute convergence. Now, in this case, this series was already all positive. So absolute convergence and convergence are the same thing. But if I had minus 2 to the k, I'd have to specify absolute convergence. More questions? Some series piss me off. Because my first hope would be, I see n as a power. What should I be able to do? I should be able to pull it out and maybe do something geometric. But I'm adding down here. Can't do that. And this is the part that pissed me off. And I should. I want to do that. I really want to do that, but I can't. Yeah.
I think that we take limit that's not infinite, rather than doing an a function of that.
Well, but if I start trying to figure out what the limit of this is, then I have to try and compare exponentials with different bases. And that bothers me. I agree with you. I think that this is going to diverge because I think the top is going to get much bigger than the bottom. But I don't know for sure how to do that limit. And that's where I started to go, well, wait a minute, limits were last semester. I should remember those. This one's hard. And I don't want to have to try and do a logarithm and then take the limit and then undo. Especially when the base isn't e. But it's almost geometric, isn't it? So let me build a comparison. I'm going to look at 5 to the n over 3 to the n plus 4 to the n, and I'm going to make the bottom of that fraction bigger. And if I make the bottom bigger, what happens to the whole fraction? It's smaller. So this is bigger than 5 to the n over 4 to the n plus 4 to the n. Yes? Made the bottom of the fraction bigger. I made the whole thing smaller. Well, now the bottom is 2 4 to the n's. Ready for the sneaky part? I'm going to rearrange that fraction. And I'm going to write it as 1/2 times 5/4 to the n. And that is geometric. Oh, wait a second. My series up there starts at 1, right? And if geometric series starts at 1, it should be a r to the n minus 1. So I should take one of those 5/4 out. And then I can say that a is the 5/8 in front. But now I have a comparison. I know that this series is bigger than this series. And this one's geometric. What do I know about this geometric series? Because? Exactly. And if that one diverges, if the smaller one diverges, so does the bigger one. My original hope, if I'd been able to pull that nth power out, would have been to use the root test. But because I'm adding in the denominator, I can't do that. I can't go directly to a geometric series, but I can go via a comparison. There are several more very good examples in this section of the text. Please read them. Tomorrow, I'm going to go back power series. Want to deal with x's in my series as well. So that's what we'll talk about tomorrow. Friday will be question and answer. I will see you all tomorrow. Have a wonderful rest of your day.